d2 acceleration due to circular motion. Now, when we had motion in a straight line, translational kinematics, we had acceleration by increasing the speed. But remember that velocity is speed plus the direction involved in the description. And we can keep the speed the same and go in a circle, change the direction. If you change the direction, you have acceleration. You don't have to go in a circle, just make some kind of turn. Just stop going in the direction you're going and just turn the wheel a little bit and you'll have acceleration. Since circular motion appears so often in physics, we're going to consider a case of circular motion and see what the acceleration would be. So let's say here we have a circle, a bead. Let's say a bead's on here, or a car driving around in a circle. All right. So we have circular motion in our vehicle. Say that the radius of the circle is big R. Now at this point, if the car here, see, traveling in this direction, if it didn't change its direction, it would end up here somewhere. But it's not. It's going to end up there. So I'm going to consider this as it fell down a little bit. If you think of this as the moon going around the earth, that the moon like fell down a little bit. All right, that's the way I'm going to think about it. All right, so here, this is a right angle, right? And this length here would be the velocity that's constant, the speed that's constant, not the velocity because the direction's changing. The speed times the time that it takes to go from here to there. It would be up there, but it's going to be a little bit lower. Okay, now that we have this, we're ready to do some math. We take R plus H, and if we square that, we have here a right triangle. So by squaring this hypotenuse, we're going to get the square of each side added together. So that's going to be R squared plus VT squared. Now I'm going to work this out. R squared plus 2RH plus H squared is equal to R squared plus VT squared. And I'll just leave the VT squared like that for now. Now we're actually going to be looking at this time being shorter and shorter so that eventually we'll be looking at something going from, say, there to there. I drew it here farther away so we can see all the parameters. But we're going to be looking at this getting shorter and shorter in time. Now notice that if we have this R, and that's going to be smaller and smaller, the H is going to be a lot smaller than the R. So the H is a lot smaller than the R, especially when we get closer and closer to this point here. If I draw that line up like that, then you see H is going to be even smaller. Okay, so that means that if we look at these two terms, say R times H and H times H, that we can neglect, we can throw this away. In fact, then the limit as we get closer and closer, and I'll just draw another figure here, just so you can see, if we have something like this, now the H, I can't even see the H because it's now, so close. So when that point gets so close there, the h is going to get smaller and smaller. So this term here will be much greater than that one. Notice that this one's going to cancel this one. So that means when that happens and we can throw this one away, we will have 2RH. 2RH here is equal to v squared times t squared. Now we're going to rearrange things. H here would be equal to 1/2, dividing both sides by 2. And dividing both sides by r, we'll have 1/2 v squared over r t squared. But now if I think about what's going on here, I remember that if I have a distance here, I'm going to travel with acceleration. So here I'm going to travel a distance h with some time t, and I find that this formula looks like this one here, 1/2 at squared, where there's acceleration. So in other words, 1/2 at squared, that means this is acting like an acceleration factor. So we conclude that the acceleration is v squared over r for circular motion. Now, this formula has been derived in books in many, many different ways. In my high school book, I remember they were doing it with some kind of similar triangles, but I kind of like this one. I found this in a book by George Gamow, and I think it's really cool that you're going in a circle. You would have been up here, but you wind up down there, and you think of it as falling, like the moon going around the earth in its orbit. It winds up here instead of there, so it kind of fell that distance h, and if it falls that distance h, remember for acceleration and distance, you have 1/2 at squared. That's your formula that we derived in the other section, 1/2 at squared. You can imagine here just falling from rest, and then you identify the acceleration factor with v squared over r, and you have your nice classic formula. So notice that the units come out like they're supposed to. Here, the velocity is meters per second. If we look at, say, units for the velocity is meters per second. And if you go, say, v squared, you would have meters squared over second squared. And then if you want units for v squared over r, you would have meters squared over second squared, and the r is meters. And that would give you meters per second per second. And we saw in the other section, an acceleration would be, for example, going something like 50 kilometers per hour per second. In other words, we have time twice in the denominator. And that's what we have here. This is meters per second per second. So that has units of acceleration. Everything checks out in a beautiful way. So that's a very important formula in basic physics. And this ends our section on acceleration due to circular motion.